Hi everyone, my name is Julia. I'm part of Group 4, and today we are presenting on parallelization in deep linear algebra, particularly in Gaussian elimination and the QR factorization method. Dense linear algebra includes many different mathematical functions, listed here, and is highly important in many different computational patterns, such as high-performance computing, machine learning, games, embedded systems, and spec, so we want to make it as efficient as possible. We want to optimize parallel Gaussian elimination and QR factorization. These optimized versions should do about the same number of flops and still get the correct answer. In serial communication, the number of words moved should not exceed the number of flops cubed divided by the square root of the catch size, and the number of messages sent should not exceed the number of flops cubed divided by the catch size to the 3/2 power. In parallel communication, we want the number of words sent to be no more than the number of flops squared divided by the square root of the number of processors, and the number of messages sent to be no more than the square root of the number of processors. I'm now going to hand it off to Thomas to talk about serial Gaussian elimination.
Gaussian elimination is something we learned in intro linear algebra and is really good for solving systems of equations. You can turn these systems into a matrix, multiply each row by a value, and subtract from other rows to get a simple diagonal matrix that solves the system. We can write an algorithm for GE using simple for loops, but it's faster and more optimized when using BLAS1 and BLAS2, which were described by Group 2. E takes a matrix A and essentially factors it into a lower triangular matrix of multipliers L and the upper triangular matrix of the final matrix U. GE can sometimes also be called LU factorization. BLAS1 and 2, which are shown in the code in yellow, are faster than simple for loops, but as you can see by this graph, using BLAS3 is even faster. The BLAS3 method splits the whole matrix into B-sized columns, shown in blue, and performs Gaussian elimination on blue. The two triangles here represent the L matrix of multipliers and the U upper triangular matrix. We then do a triangular solve function on the pink region of the matrix using LL, and then multiplies the pink and blue regions and subtracts them from the green region to update the trailing submatrix. We continue this process with subsequent B columns until we have simplified the whole matrix. This method meets our communication lower bound goals for really big and small matrices, but fails to meet the messages sent goal for medium-sized matrices, so we must use recursion in those cases to meet these goals. Even though this method is faster than BLAS1 and 2, it's still not as fast as parallelization. I'm going to hand it off to Ife to talk about parallel Gaussian elimination.
In the parallelization method, Dr. Demo outlines 6 possible data storage structures for the matrix. The 2D cyclic block is the best as it divides the matrix into BXB submatrices, and each column is controlled by P to the 1/2 processors. This structure minimizes idle time and best allows us to reach our communication optimization goals. The parallelized method is very similar to the BLAS3 method. In steps 1 to 3, we look at our tall, skinny submatrix B, find its maximum entry, move it to the top of the vector, and broadcast to the rest of the matrix that we made this switch within B. This is called a pivot. From there, we do Gaussian elimination on B, use LL to triangle solve the pink region, as shown in step 8, multiply the pink and blue regions, and subtract from the green to update the trailing submatrix, then repeat this process with subsequent B vectors. This method is faster than BLAS3, but because there are so many pivots, one for each B submatrix we evaluate, we have to send a lot of messages updating the vector and therefore fail to meet the messages sent communication goals. We can fix this problem using tournament pivoting. Basically, we take our big matrix and divide it into submatrices. In this picture, they divided it into 4. In each of these submatrices, we do a classic Gaussian elimination and choose the best B pivot rows from that submatrix. We combine the best B rows from the submatrix 1 and 2, and from 3 and 4, and do another Gaussian elimination within these two combined matrices to get the best B rows from each group. We continue this process of combining and Gaussian elimination until we are left with one group of the best B rows in the whole matrix. These rows are moved to the top of the original matrix to perform Gaussian elimination with no pivots, decreasing the number of messages sent and allowing us to meet our communication lower bound goals. This logic can also be extended to QR factorization. So by eliminating pivoting from our operations, we can speed up the Gaussian elimination process. But it's possible that we can go even faster by using multiple copies of the data at once. I'm now going to hand it off to Alexa to talk about these multiple copies of data.
Using C copies of the data in simpler algorithms like matrix multiply decreases both the number of words and the number of messages sent. In GE and QR factorization, however, using multiple copies of data decreases the number of words but increases the number of messages sent. Therefore, we need to optimize C to get the best combination of words and messages in the algorithm. This graph shows on the right that the scale-pack algorithm alone, the parallelized method that did not use tournament pivoting, is furthest from peak performance. Scale-pack with tournament pivoting operated slightly closer to peak performance, and scale-pack with tournament pivoting and multiple data copies performed closest to peak. In the graph on the right, the left group of bars shows tournament pivoting with and without multiple data copies, and the bars on the right shows classic pivoting with and without data copies. One data copy without tournament pivoting takes the longest to compute, while multiple copies and tournament pivoting takes the least amount of time. And finally, what improvements have we made in this technology, and where do we see it going? I'm going to hand it off to Karen to talk about this.
In the top columns on this graph, the bright green shows the theoretical peak speed, the brown bar shows the realistic peak speed, 66% of the peak, and the black bar is the CPU speed alone. The middle group of bars shows the speed of the matrix multiply. In the first version of BLAS, released in 2007, we can see faster speeds than CPU computing. But BLAS 2.0, shown in brown, is much closer to peak speed. In more complicated algorithms like GE or QR factorization, as we can see in the bottom group of bars, both BLAS 1.0 and 2.0 aren't that great at increasing processing speed compared to the CPU in black. People eventually determined that the two main bottlenecks slowing these algorithms down were pivot time and not properly splitting up work between the GPU and the CPU. For example, BLAS 1 operations should be done using the CPU, while the BLAS 2 and 3 operations should be done on the GPU. A new method for fast matrix factorization transfers data between the CPU and GPU to optimize which work is done where. As you can see by the blue line on this graph, this method has increased algorithm speed greatly. Now, looking back at this bottom group of bars on the second graph, we also see that Gaussian elimination and QR factorization efficiency have greatly improved using this new method. We are much closer to that 66% as determined by the top brown bar. Rachel will now talk about the conclusions of the presentation as well as the connections to our class.
So in conclusion, research has allowed us to identify a realistic peak in computing speed for GPU architecture, and by transferring data between GPU and CPU, we have been able to increase efficiency in both matrix multiply and other functions in LabVAC, such as Gaussian elimination and QR factorization. This connects to what we've learned in class because, throughout this course, we've learned about several algorithms and their respective computing times. It's important to understand how variations in these algorithms affect computing times and how to interpret and read the graphs we have produced in respect to running different algorithms. For example, let's go back and review the algorithm for Villette implementing the neighbor list. This algorithm dealt with searching for all neighbors of a given molecule. Over several time steps, the list of discovered neighbors was used to evaluate force and energy. However, the algorithm also had weakness in its efficiency if its list became too large. And finally, we have 3 discussion questions. Our first question is, How does increasing the number of copies of data affect the lower bound communication goals of simpler algorithms like matrix multiply versus harder algorithms like Gaussian elimination and QR factorization? Our second question is, which matrix organization structure should be used in the parallel Gaussian elimination method, and why? And lastly, our third question is to rank these methods slowest to fastest. Serial GE using BLAST3, parallel GE using tournament pivoting and multiple data copies, parallel GE with no tournament pivoting and no data copies, serial GE using BLAST1 and 2, parallel GE with tournament pivoting and no data copies, and serial GE using simple for loops. And thanks for listening.